Hello student, now we are going to find out the electric field due to a second case where we are having a wire of infinite length which extends from minus infinity to the plus infinity, and we are finding its electric field at this observation point P again by using the Gauss theorem. The steps involved are same as what we have done earlier in case of a single point charge. Now one thing, because wire is infinitely long, so we cannot find how much total charge is present on it. But we assume that the wire is infinitely long and it is uniformly charged wire. This means that every unit length of the wire, every 1 centimeter portion of the wire or every 1 millimeter portion of the wire is having the same amount of the charge. So what we do, we define linear charge density for the wire indicated by the symbol lambda. So what we do, we consider a small portion, small length of the wire, and we name it as length L. So if this length L holds a charge Q, Q is not the charge on total length but only on this particular length L of the wire. In that case, lambda will be equal to Q over L. Okay, now we want to find out the electric field. So first step over here is to draw the Gaussian surface. As told earlier, Gaussian surface matches the shape of the charge distribution. We know that a wire is cylindrical in shape, so its Gaussian surface will also be a cylindrical in shape. In order to do that, we join the wire with the point P, and this is the distance R between the two. So what we have to do, we have to generate a cylinder around it. In order to do that, the cylinder will be of length L and the radius R, with the axis of the cylinder passing through the wire. This is the Gaussian surface, which is cylindrical in shape. Now, in case of field due to a single point charge, we defined only one area element. But in case of this cylinder, we will define three area elements because there were only one surface. Now there are three surfaces which are involved. One, which is the first cross-sectional surface of the cylinder, second cross-sectional surface of the cylinder, and third, the curved surface of the cylinder. So we define an area element around the point P, which is perpendicular to the surface. Second, on the top over here, anywhere over here, same surface area dA normal to the surface. Third surface area onto the second case, lower cross-sectional surface. It is perpendicular to the surface pointing in the downward direction. So because there are now three surfaces, so we have to calculate the flux through the three surfaces. So if we apply definition of the flux, total electric flux which is emanating or passing through the surface of cylinder, it is equal to E dot dA, integral for the first surface, second surface, and the third surface. We take it as the first surface. This is our second surface. This is our third surface. Now we already know that field due to this positive charge, it is perpendicular to the surface of the wire. So its electric field will also be perpendicular to the surface like this. If we indicate the field for the second and the third surface point, it will be over directed in this direction. For here, it will be directed in this direction. So we see that electric field only for the curved surface, it will be in the direction of the area element, but for the second and the third surface, it is perpendicular to both of them. So if we expand the equation, what we are getting, that total flux phi is equal to EdA cos 0 for the first surface plus EdA into cos 90 for the second surface and plus EdA again cos 90 for the third surface. So this is for the first surface, second surface, third surface. Cos 90 is 0. These two will be equal to 0. So phi will be simply E into dA. Again, E is the constant on the Gaussian surface. It will be outside the sign of integration. Integral will be only for the surface area of the cylinder. Okay. So phi, it will be equal to area of the curved surface. dA is the area of the curved surface, not the total area of the cylinder. So total area of the curved surface, it will be equal to 2 pi r into L. Okay. Also, using Gauss theorem, phi is equal to Q by epsilon naught. So if we compare these two equations, E into 2 pi r L is equal to Q over epsilon naught. If we compare, E is equal to 1 over 2 pi epsilon naught Q over R into L. But we know that Q is not provided to us, so we cannot leave the final expression in terms of Q, but we know that this Q divided by L is a linear charge density, which we already know. So it will be equal to 1 over 2 pi epsilon naught lambda by R. Or you can also multiply and divide by the 2 in order to express the final result as E equal to 1 over 4 pi epsilon naught 2 lambda over R. So lambda is a constant quantity, 4 pi over 1 over 4 pi epsilon naught is also constant. So this indicates electric field is inversely proportional to R. So as we move away the observation point from the location of the wire, R increases, the strength of the electric field decreases. That is, if we plot a graph between field and the distance on the either side of the wire, this is the distance R, this is a distance taken on the wire toward the right side, or it can also be taken on to the left side. This is the electric field. Maximum field will be on the cylinder. Suppose this is the maximum value of the field, and after that, as R increases, the value of the electric field will go on decrease. So we will get a symmetric curve on the both the sides, and these curves always keep approaching towards the distance axis, and where they are going to meet at the x-axis at the infinity, because only when R becomes equal to 0, R becomes equal to infinite, then electric field will become equal to 0. Thank you.